Hello, everybody. Dr. White back again with the Poisson distribution. So think back to Bernoulli processes, okay? So that's a sequence of Bernoulli trials. They're all independent. Chance of success on each one is the same. And this time I want you to think about like the success as something distinguished, as like an event that maybe you've been waiting for. And so you're like, blah, failure, woohoo, success, blah, failure, woohoo, success, and so on in this process with no fixed end. So that's a very discrete thing, you know, first trial, second trial, third trial, fourth trial, fifth trial, you know, natural numbers, discrete-ish. As opposed to you know, like the real numbers, like intervals, real numbers, which, you know, are a continuous thing, kind of like our perception of time. In fact, if you kind of put time on a real number line, so here's like time 0, when you start watching something. And as you go through watching, you've watched for an hour, you watched for 2 hours, you've watched for 3 hours, you could keep on watching forever as I, you know, move my little crosshairs over. You might see events occur. And so it's like starting at time 0, boredom, woohoo, boredom, woohoo, boredom, woohoo, boredom, woohoo, and so on. You know, events occur. And we would like to work up a kind of mathematical model for this process of watching for events over something continuous, like time. So let's suppose that the process has these 3 properties, okay? First of all, that the number of events in disjoint intervals of time are independent. So like the fact that there's been 3 events here in the first unit of time doesn't affect your estimate of the chances of how many events there are going to be in the, say, the second hour of time, you know, from 1 to 2, or anything like that, okay? Secondly, imagine a very small number h, some small positive number h, and think about some time t and look at the time interval from t to t plus h, okay? And so if h is small, then that's only a tiny time interval, and there might not be much chance of seeing an event during that time. But suppose that the probability of getting exactly one event during that time interval divided by the length of the time interval, which is h, suppose that the limit of that is lambda. And so I've kind of badly written it here. This bar, you know, sorry, I can't quite isolate the bar. This dividing bar should not have gone underneath the limit sign. It's supposed to be the probability divided by h and then take the limit of that. You know, suppose that converges. Suppose that limit exists and call it lambda, okay? So lambda is just some fixed and positive real number. So kind of what you're saying there is that when h is small, the chance of one event in the interval from t to t plus h should be approximately lambda times h. So lambda is a kind of a rate, as it were, at which events happen in this process. So suppose that happens. And number 3 here, suppose that the chance of at least 2 events in a small time interval is basically 0. So more formally, the limit of the chance of 2 or more events in an interval from t to t plus h converges to 0 as h goes to 0. If all that happens, then we say that our process is a Poisson process with rate lambda, okay? And again, I stress that we think of lambda as a rate because of that limiting fact. Because the limit of the probability over h is lambda, then the probability would be about lambda times h when h is small. Chance of an event in that little time interval is about the length of the time interval times the rate. And now let's focus in on any unit time interval. So it could be this time interval from time 0 to time 1, but it could be like from time 2.3 to time 3.3, any interval of unit length, okay? Focus in on that interval in your mind and define a random variable for yourself. Let x be the number of events in that unit time interval. That's going to be a random variable, a discrete random variable. Its possible values are 0, 1, 2, 3, 4, and so on, and more events. Such a random variable is said to have the Poisson distribution with rate lambda. So can we find the probability mass function for this distribution? Well, here's my idea for handling this. Take that time interval from 0 to 1, that unit interval, and divide it into a very large number n of equal length disjoint intervals. So here would be a picture, right down here, would be a picture of such a division. So the number 0 is 0 over n. The first interval extends from 1 to 1 over n. The next one goes from 1 over n to 2 over n, all the way up to, like, here's the ith interval from I minus 1 over n to I over n. And then finally, the last interval is n minus 1 over n to 1, which is n over n. And so that's n subintervals. They're all the same length, 1 over n. And if n is large, they're all very small, okay? Well, you know, the number of events in that whole 1 hour interval, I claim, should be approximately a binomial random variable. This Poisson is approximately a binomial random variable with n trials and chance of success lambda times 1 over n. Why is this so? Can I convince you of this? Well, each of these time intervals you can think of as like a trial. And in each time interval, you can either have an event or not, okay? And remember, the chance of 2 events in one of these tiny time intervals is essentially zip, okay? And so you're either looking at 0 or 1 events in the little time interval. So each time interval is like a little Bernoulli random variable. And what would be the chance of success? Well, according to property 2 up here, the chance of success is going to be about lambda times the width of the interval. So lambda times 1 over n. And so you're adding, and so, you know, if you add up those n Bernoullis, they could make a binomial if they're all independent. Are they independent? Yeah, because of property 1 up in the definition of a Poisson process. The number of events in disjoint intervals are independent. So if I get an event, say, in this second interval here, that doesn't affect the chances of getting an event in any other interval. So we're looking at the sum of n independent Bernoullis. We're looking at a binomial. That's only approximately the case because, you know, the 1 over n length is only small. It's not 0. And so we have approximations there for those probabilities. But the probability that the Poisson is x, the probability of x successes, would be approximately the probability that a binomial with that number of trials and that chance of success would have x successes. And so there's the formula for a binomial. Here's our p, lambda over n. Here is our, well, here is our 1 minus p. So it makes intuitive sense, and you have to do more mathematical work, you know, kind of graduate school work to really nail it down formally. But it makes intuitive sense that the probability of exactly x events should be the limit as n goes to infinity of this expression here. So I look at this limit, and I stare, and you know what? I'm kind of, this little bit right here that I'm circling with my mouse, it reminds me of something from Calc 1. Do you remember in Calc 1 when you did L'Hopital's rule? And one of the applications of L'Hopital's rule was this cool limit fact here, that the limit as n goes to infinity of 1 plus r over n to the n, where r is just some fixed real number, but n is going up, 1, 2, 3, 4. The limit as n goes to infinity of that turned out to be e to the r. And so I've got something like that going on here. I've got a 1 plus minus a real number, and it, like an r over n, but it's a lambda over n. And I don't quite have an n here, but I got an n minus a fixed number, x. And I'm taking the limit as n goes to infinity. So that looks really similar to this expression down here on the bottom. So what I'm going to do is I'm just going to manipulate my limit expression a little bit to see if I can exploit that L'Hopital's rule fact. So I start with my limit expression here on the top. And I look at the combination expression first. And what I'm going to do is factor out the x factorial that's present in the top and the bottom. N factorial is n times n minus 1 all the way down to 1. X factorial is x all the way down to 1. And so, I'm sorry, n minus x factorial is n minus x all the way down to 1. And so what I could do is factor out from it, what I could do is cancel out from the top and the bottom all of the factors from n minus x down to 1. So the x factorial is still going to be left on the bottom. I'm not touching it. But the top, I'll start at the n, and I'll only be able to go down to 1 more than n minus x. Everything else got canceled out by the n minus x factorial. So I've got this expression here. Now I'm going to leave lambda over n to the x alone. And I'm going to leave the 1 minus lambda over n to the n minus x alone as well, for the moment. But then I'll take a look at them. And I'm going to write this lambda over n to the x as lambda to the x over n to the x. And I'm going to move the n to the x underneath those other factors. And I'll move the x factorial to be underneath the lambda to the x. Okay, and I'm also going to use a property of exponentials to split up this last power here to be 1 minus lambda over n to the n times 1 minus lambda over n to the minus x. And now I'm going to think about what all of the pieces of this product are going to as n goes to infinity. There's a fixed number of pieces, There's x pieces here. If I just break it up, if I take the n to the x and just put x separate n's on the bottom, and then stick the various factors on top of the n's. That's a total of x pieces right there. And then there's another piece here, lambda to the x over x factorial. And then there's this piece here, and that piece changes as n changes. N's going to infinity, so that piece is changing. And then I've got 1 minus lambda over n to the negative x, and that piece is also changing because the n's going to infinity. But let's think about their limits. N over n is actually just equal to 1. I'm sorry, yeah, it's equal to 1. Now, n minus 1 over n is not equal to 1, but as n goes to infinity, it's definitely going to 1. And n minus 2 over n that's not written is definitely going to 1. And n minus x plus 1 over n, that has to go to 1 too. Even if x is a really big number, still, n's getting bigger and bigger and bigger. X is just staying what it is. N's what's getting bigger here in the limit. And so you basically get big number over slightly bigger number on the bottom. So that ratio is also going to 1. So those x factors, they're either all 1, like the first one is, or they're going to 1. The lambda of the x over x factorial, that equals 1 all the way. And this, I can use my L'Hopital's rule fact. I think of it as 1 plus a negative r over n to the nth, and that comes to e to the negative r. So we got an e to the minus lambda here by L'Hopital's rule. Now this piece, this last piece, I've got a fixed power of negative x. But what am I raising to that power? 1 minus lambda over n. N's headed to infinity, so 1 minus lambda over n is headed to 1 minus 0, which is 1. And 1 to the minus x is 1, because 1 to the anything is 1. So all of the separate factors limit out to something that multiplies to lambda to the x over e to the minus lambda over x factorial. Now the limit of a product is product of limits, so this expression here really is the limit. Pretty neat. So that's the probability mass function for a Poisson. Totally worth memorizing. It's fun to get the moment generating function for a Poisson. So let's do it. It's the expected value of e to the tx. So it's the sum over the possible values, 0 events, 1 events, all the way up, of e to the tx times the PMF. Now I stare at the sum, and e to the minus lambda doesn't change as x changes, so I pull it out by the distributive property. And I can also use some exponential properties in the way I've been using them lately to take the e to the tx here and the lambda to the x here and write it as lambda times e to the t to the x. Still got my x factorial on the bottom. And then I stare at that sum. And it reminds me of the Maclaurin series for e to the x from Calc 2, where you learn that e to the x is the sum as an index goes from 0 to infinity of x to the index over the index factorial. This time my index is an x, and what used to be an x here is a lambda e to the t, but it's still the same thing. That sum must be e to the lambda e to the t. So I've got e to something else, multiply together, so that's e to the sum of those things. I can factor out the lambda, and I get e to the lambda e to the t minus 1. That calculation is good for all real numbers t. So this moment generating function is defined for all real numbers. And of course, we can use it to get the expected value and the variance. So derivative of the moment generating function, well, let me see. It's a chain rule thing. So I won't do that again. Well, let me try it. And let me try this. Well, no, it still doesn't quite work. And I don't know, there's all these like bars there now. I don't know what's up with that. Anyway, take the derivative. Derivative of e to the stuff is e to the stuff times derivative of the stuff. And the stuff is a constant times e to the t minus 1. So it's constant times derivative of e to the t minus 1, which is e to the t. Plug in 0, work it out, and you get lambda. The mean of a Poisson is its rate, which totally makes sense. You know, the expected number of events in unit time should be the rate at which events occur per unit time. If you get lambda events per hour, the expected value of the Poisson should have been lambda. Great. Similarly, you can take the second derivative. You'd have to use the product rule for it. Plug in 0. And then your shortcut formula for variance, second derivative is 0 minus the square of the mean, will end up having you cancel out that lambda squared you see. And this is interesting. The variance of a Poisson is actually the same as its mean. It's lambda. So that's pretty cool stuff. What we ought to do is some computations with Poisson random variables maybe in another screencast. So I will see you soon.